Okay, in this session, guys, we're going to be talking about steel heat treating. And in this lab, you're going to be working with two different alloys of steel. One's going to be an alloy steel, probably 4140 typically we like to work with, and the other steel is going to be a tool steel, and we're probably going to work with A2, which is air hardening tool steel. So when we start thinking about the heat treating of these steels, we want to look at commonly used tools steels and alloy steels that are used in industry, and these are both great candidates to kind of work with that are going to help you when you get out in industry. So let's do a quick review here. We know that from our previous labs dealing with phase diagrams and everything, we've already conquered what a phase diagram for an iron carbon diagram looks like here, where we have the percent carbon by weight down here, and we know that this is our eutectoid, typically around a 1080. Still, we know the hypos are over here and our hypers over here. But what I want to do is talk a little bit about temperature and add some more emphasis on temperature. So things you need to make a note of is we have a term that we typically reference as upper critical. Now that talks about a line referencing A3 and ACM. So on this diagram, right here is my A3 line and here's my ACM line. What are we saying here? If we go above that, we're going to become austenitic, this gamma phase right here. So that's when our steel is in that phase. And that if we go above that line, we're going to austenite. That's going to erase all effects of any other heat treatments, things like that. We're going to see grain regrowthing. Remember our grains being regrown. We talked about that in recrystallization. So upper critical, definitely above these temperatures here. The lower critical is known as A1 line. Now that's this line right here, okay, A1 line. Now what we're talking about here in A1 is basically the eutectoid line. Some people may reference to that. When we go above that line, okay, we're no longer going to be, we're going above the up or lower critical temperature. We want to stay below that. So if I'm going to do something like a coating or a plating and they're going to use heat, and let's say they go up to 600 degrees Fahrenheit, then what they're saying is it's a lower critical process is how we would use that in terminology, saying that we're a lower critical. We didn't go above that, so we're not seeing any austenite coming out of solution or any real effects on the material. So a lot of times we talk about lower critical. So upper critical, lower critical. And the other thing I just want to point out here is an A2 line, which right here you have an A2 line here, and then from over here you have an A2. And basically what are we saying happening at A2? That's our Curie point. That's the point that the material is no longer magnetic. And we've kind of talked about that in a prior lecture as well. So let's talk about heat treatment here. Heat treatment, a lot of people think it's we're heating it up and making it harder, making it stronger. Yes, we're doing that, but we also can come in and anneal it. So annealing is where we heat it up and slow cool it, and we get that full green regrowth and recrystallization. And that's considered a heat treatment process. Austenizing, that's where we take the steel and we heat it up above that upper critical temperature to get austenite. Now here's the catch, and I put this on here because a lot of our textbooks don't have this in there, and this is just a rule of thumb right here, that if I have a small part, something maybe a 1/4 inch, I can hold it in the oven for about 30 minutes and it will soak and the heat will go throughout and we'll get a full austenitic structure if we're at that temperature. Now if I take a part that is 4 inches in size here, I need to probably hold it for 4 hours. So for every 1/4 inch, maybe I want to do another 30 minutes on there. So that's just kind of a rule of thumb. Again, sometimes in the heat treaters guides, they'll actually help point out some of that with various metals. So one of the things we need to think about is what size is our part and how many minutes we have that. So it's not just that we're telling you to leave it in the oven for 30 minutes. There's good rules of thumbs to make sure we're getting the phase changes that we need. Now, another thing that we've talked about is this wonderful isothermal or TTT diagram, time temperature transformation. And we talked about the fact that when we quench something, we want to get in front of this curve right here, the nose or the knee of this curve. And the more carbon we have, it moves it to the right. And we want to get martensite start and finish so we can get primarily a martensitic looking needle structure that's feathers. And that's going to be this good, strong stuff. That's why we would like to heat it up and quench it. okay? And you guys remember the martensite. That's the stuff that's going to be really hard, needle, feathery, white feathery look, and we've seen some of that with the previous labs in phase in the Jomini lab, to be exact. Now, when we take a piece of metal and we put it in the furnace, and we're above the upper critical temperature, so we take some steel and heat it above 1600 degrees Fahrenheit, what we're going to see is that metal is going to get red hot. Colors indicate something. So red hot is typically known as above 1600. Blue is around 800 degrees. So we have straw, we have all these different colors. Once we get it hot, we need to quench it. And one of the famous things is probably taking it and quenching it in water. So if I dump that piece of metal in a bucket of water, it is not going to cool immediately. What happens is it's going to form a vapor blanket, a steam blanket around the part, and it's going to get bigger and bigger, and then eventually it's going to discharge, and then we're going to actually cool the metal. So let's look at this chart down here. We have the stages of quenching here, and the first stage, when we put it in there and it forms that vapor formation, it's not really doing much cooling here, okay? When does it get to cooling? That's this stage right here, the third stage, which is C, vapor discharge. That's where that discharge of the vapor barrier is happening, okay? And that's where we see that dramatic quench rate right there. So when we first put that sample in there, it can develop that insulative steam blanket around that vapor barrier, okay? Now, how can we break that up? Agitation. When we put the sample in there, we could agitate it and break it up, or force fluid at a flow rate and discharge that vapor barrier, and it would quench even faster if we wanted to do that. So, severity of quench. What are we going to quench this thing in? Well, we're going to take this and we can quench it in a lot of different stuff. Let's talk about 4 major categories here. We could quench it in air. Okay, we're going to be working with A2 series. That's an air hardening steel. So that is the lowest severity. We're going to find some advantages. We're going to talk about that. Some of our steels that we're going to work with are going to be an oil type quench. So we can quench it in oil. If you watch Forge and Fire, they do that, and it's nice fire coming up. And that's a medium severity quench. And there's even different levels within each category of how we do these things. Water is a high severity, so we're going to see a high severity, a high rate of cooling coming out of that. And one that's best is probably going to be brine. That's your saltwater solution. So that's going to have our highest severity. Again, we can change the severity of quench by agitation, and that's going to increase the cooling rate. So if we have air, we can blow air faster across it, and it will increase the cooling rate. So more severe quenches cause deeper hardening. So if I want a deeper through hardening effect, I need to probably look at brine or water. Let's talk about these different quenching medias. Water is great because it's very cheap. It's all over. We can dispose of it fairly easy. Again, I say dispose of it. I have seen issues where we do a DEQ or EPA audit and they say you're quenching materials with chrome in it. Is that chrome leaching into the water? We'll take samples and test it, and we're going to have to deal with those. So you want to kind of double check and make sure you're not doing anything to get yourself in trouble with just dumping that water down the drain. Now the problem is, can cause internal stresses, distortion, and cracking. This is big. Not all steels can I take and quench in water. Some steels, you do that, it will quench crack. And we're going to talk about that in some later slides here. Let's talk about oil. This is the medium quench. It's a lot more gentle. Sometimes we in the heat treaters world, in the metallurgical world, we say it's a safer quench. It's a safe metal for quenching. If it's a safe metal for quenching, then you could probably quench it in water and it's going to be just fine. If it's not a safe metal, then you may not want to do it in water. So sometimes we use that word safe in there and gentle. So let's look at some of these things. Here you have oil, the flash point, things like that can happen. We can have fire, so we need to really worry about that. There's going to be less distortion here from the parts and probably less stress, so we're not going to see that material wanting to move and change shape. That's going to be an advantage for us, and definitely not having cracks. If we use air, now I've got a little part over here, and we're using a fan underneath. A lot of times we can have a table that's got a porous structure that will just hold the part, minimizing the contact. And we will see in the heat treaters guides and some of our stuff that we want to cool evenly on all sides. So if we put this on a piece of aluminum, we would be changing the rate of heat extraction on the bottom versus the other sides. So here we can have the air coming through there, or just set it on there and let the heat come up and rise by itself. But this is going to be a very gentle solution. If I take some stills and I quench it in air, they're really not going to get that hard because they're not air quenchable. So we're going to have to, again, identify what stills are quenchable by water, air, and oil. Now this is a neat little plot right here. This is your TTT diagram, and this is just kind of showing the effects of different quench media. Being a faster quench, I could get in front of that nose of the curve real easy. Maybe even an oil quench, not as easy. And I can end up with these structures: martensite, bainite, and perlite. Martensite's hard, bainite's hard and tougher, but not as hard as a martensite. And then we could have a little bit of fine perlite that would be picked up. If we were to come in here and do a furnace cool, leaving it in the furnace overnight, then we're probably going to get coarse perlite. So that kind of shows an example of some of the structures we might could see from a typical stress strain or a TTT diagram. This diagram, what are we looking at here? Temperature of media and quenching. So if I have oil, is the oil at 120 degrees, 200 degrees? The temperature of that quenchant that I'm going to quench in is going to change the cooling rate as well. So I may need to have some method, and I think this slide is going to kind of speak about this. Let's say that I take a part and I quench it in a tank of water, and that water's a gallon. And then I quench another part in there and another part. What's going to happen over time is that water temperature is going to rise. So I need to have a method of extracting the heat out of that water. So maybe I need to have a circulatory pump that's circulating water through a radiator and extracting that heat to maintain it maybe at room temperature here. Okay. So that could change as the process changes, my water temperature changes. Very important to keep that quenchant media the exact same rate. It may be that our shop is a shop that in the winter it gets really cold right here, and that's going to change our quench rate. So I may not want that variability in my process. So maybe I need to have a heater heating that quench water, a stock tank heater or something, keeping that water at room temperature. This slide, I put this on here just because this is a gear profile, like a spur gear, and we would heat it up probably through an induction method, and then we would quench it, and you have a thinner mass here than this core, and what's going to happen is we're going to see the discharge, so we'd want a discharge vapor disruption happening, but the cooling rate is going to change, and we might see it being very hard due to the quenching rate on the outer surfaces here, and have a tougher core due to the heat rate not coming out as fast and pulling the heat out of the part, keeping this core of this tooth hard. So we would want to get all that under control in terms of our quenching rates, the quenching temperatures, the agitation that we do, as well as the shape of the part. Now we're talking about shape of part, and I put this little setup here for you guys. Hardness versus penetration. If I have a 1/2 inch part made of 1045 steel, and some of you guys have already looked at some 1045 steel when we looked at phase diagrams. That's a hypoeutectoid steel. When we look at that, it's really easy to get it fairly hard because it doesn't have much mass there. But as I get a part that's bigger, so let's say I come down here to a 4-inch part right here, and I heat it up to upper critical temperature and I quench it correctly. Let's say we're quenching these both in water. I'm only going to see that surface of that part being around a Rockwell C30 versus that 1/2 inch part being up over 55, close to 60. And so what am I saying? I will never get the bigger part as hard as that smaller part because the effects of thermal mass. Now, over here we have a 6140 steel. This is an alloy steel, and because the alloy's in there, it may change the through hardenability, which makes it easier to get harder values in larger part sizes. Again, effects of thermal mass. When you're looking at the heat treaters guides, you might look for sections of effects of thermal mass or quench rates on part sizes. When we start talking about quench rates, and we talked about the fact that the different quenchants are safe, the metal could be a safe quenching, we could dump it in water and it's going to be fine. It won't quench crack. Some metals will quench crack in water. What's happening is when we quench that, the outer layer of that material is going to be in what? tensile. And the tensile forces on it, because the inside is incompressive, is going to exceed the material properties, and we can actually develop a very small hairline crack. Now, these are all big cracks, and yes, you can see these, okay? We can see these big, beautiful cracks. And I want you to look at this part. See this transition from this area right here? Those stresses localized at that concentration point and cracked out. So this part would be very susceptible to quench cracking. So changes in cross section, or if we have a thick and a thin section, yes, we can have quench cracks develop in those parts really, really easy. So that brings us to another part of the lab that we're going to be doing is going to be doing dye penetrant testing. This is a non-destructive test. We're going to be taking some of our coupon samples of the alloys. We're going to heat them up to austenite temperature. We're going to quench them in different quench methods. And then what we're going to do is we're going to have these 3 cans of dye penetrant testing. You can buy these at a typical weld shop. They do a lot of it for welding to see if cracks weld next to the weld. First method is there are standards of how you do this. Typically, you have to have a rag that it has lint free that won't put lint out, and you're going to have to clean and degrease the part. So typically, we're going to clean the part and get it totally clean with the cleaner there. Okay, so step 1 is clean the part, and once we get it clean, what we're going to do next is put the dye on there. That's this red can, dye penetrant, and they use red. They do have other colors, but typically red is the most predominant color that we see out there, because it catches your eye really easy. And you're going to coat that part just like this picture here. You're going to soak it pretty wet, and you're going to let it sit for a period of time. Now, you're going to do all this probably at room temperature, 70 degrees. You don't want to do it at freezing temperatures because the viscosity of the materials are going to change. And so you want a material that has a low viscosity that will soak into the cracks, okay? It's going to allow it to wick into those cracks that we can't see. And then what we're going to do is take that rag and wipe that surface clean, get all that dye off. You don't use the cleaner to do that because you can flush and irrigate out the cracks with the cleaner. So we clean all this off with a rag, get it done up, looking right. If we do use cleaner, some of the standards will allow you to put cleaner on the rag, not on the part, but on the rag, and then apply it and do a light wipe real quick. In our lab, we're not going to use any cleaner after the dye penetrant. You're just going to use a rag, okay? Now then, the next phase is developer. This is the stuff that's kind of like the foam white stuff that you would spray on windows to draw Frosty the Snowman, you know, all that kind of fun stuff. It's just a developer. And what it's going to do is you're going to come in here and put the developer on the part, and it's going to dry. And this has a agent that is going to have an affinity for that dye, and it's going to pull the dye out of those cracks, okay? And so if there was dye to go in that part, I will really see these cracks stand out from the dye bleeding out and being pulled out by that developer. And so we can see those quench cracks happening there. Then I can just wipe all this off and we could go from there. So we will be testing materials, quenching them correctly and incorrectly, and doing this dye penetrant and seeing if there's a change. Now, we talked about hardening the material and getting it to full martensite. The other point that we want to talk about is tempering that martensite. Martensite is going to be nice, sharp BCT. That's that body-centered tetragonal long crystals. It's going to give the material the strength that we want. And then what we can do is come in and temper it. Now, what is tempering? That's where, again, look, here's that A1 line. A1, we're going above the lower critical temperature. So we're getting up. We're not up to the upper critical, but we've passed that lower critical temperature. And what's going to happen is those elongated BCT structures, those long needles, are going to start rounding off and shortening up. And that's what we're seeing here in this view, this tempering of that. And what that's going to do is make it not as hard, and it's going to be tougher, but it's still pretty hard. It's tempered martensite. So eventually, if we start tempering the martensite so much more, we can start going back to whatever structures are before. If it was perlite, ferrite, and cementite, we might see those kind of things developing back from heavy tempered martensite. Again, in the heat treaters guides in the very bottom, they'll have examples of steels that were heat treated, tempered, and what the microstructures might look like for the different treatments there. So let's look at one more slide, a couple more slides here. The effects of tempering temperature on hardness. So this is a generic graph, guys. Don't use this for your lab. You're going to go to the heat treaters guide. This is an educational slide here. We have Rockwell C hardness. 60 is hard. A file is around 60. That's really hard. We've talked about that before. If I come in here and I temper it and I raise that temperature, again, what do we say? The 600 is our lower critical, under the lower critical temperature, then if I do that, okay, my hardness really isn't going to change that much. It changes some because we are seeing some elevated temperatures, and again, it depends on the steel. Every steel is going to be different in terms of tempering, so we need to go to the heat treater's guide and look at that and establish that. Now, if I heat it up above that temperature, up to above critical temperature, then I can see the reduction of that martensite structure happening potentially. This is the last slide, and let's talk about this before we get into the heat treater's guide. The thing is, how long do I leave the part in to soak? We talked about 30 minutes per quarter-inch section on a part to austenize it, and then we could quench it. And now let's say we want to temper it. So I'm going to put it in the oven, and I can still use that 30 minutes per quarter-inch cross-section formula, but how long do I leave it in the furnace? I need to leave it in there for some period of time. Okay, this is in hours. Now, if I leave it in the furnace for 4 or 5 hours, I forget and I go to lunch and I come back, I am not going to see that much happening here. Now, this is assuming we have a fairly large part. It takes it some time to get to temperature, and it finally gets to temperature, let's say after 3 hours. Maybe that's our 3-inch, 4-inch diameter piece of material, and I forget a few more hours. It's not going to have that much effect on there. It will have a slight effect, but there's not enough energy there to do any more change. So that's just a neat kind of feature. So let's go look at the heat treater guides on some materials. Okay, if we're working with 4140, I'm in the novel, The Heat Treater's Guide for Ferrous Materials. So you can find that link in our Canvas site under Course Links. Go to the Ferrous Materials under the Heat Treater's Guide and search for 4140. Now, we've kind of looked at this in past lectures, and I wanted to point out a few key things for us at this time. Fully hardened 4140, you're talking Rockwells of anywhere from 54 to 49. That's pretty hard. That's pretty good stuff. Now, that's not going to be as good as what we're going to see in our tool steels, the A series. This is the alloy steel. It does talk about how to anneal it and how to harden it. So we're going to austenize it. That's above the upper critical temperature. And it says right here to quench in oil. So we'll discover if that's good advice or not in this lab. And you can reflect on that. Now, to temper it, we're going to temper it to the desired hardness. Now, it doesn't tell you how to do that. We've talked about our isothermal diagram there. There's our Jomini quench data. We've done that in a previous lab, but let's look at some new stuff down here. Some things that we can have down here is basically as quench hardness. Remember, we talked about the effects of thermal mass. If we have a 1/2 inch versus 1 inch or a 4-inch part, we talked about the fact that maybe if I have a small unit that we built and it was made out of 4140, the parts, and we heat treated it and we got that surface to a 57, the center of it's going to be fairly close because it's a small part. Now, let's say we decide to upscale that in a sales meeting and we're going to go to a 4-inch size part. We heat treat it. The best we're going to get out of that part is probably going to be around a Rockwell C36. So if we were still wanting that hardness and the properties associated with that, we're probably going to have to look for a different steel. So this is a nice deal that kind of gives us a little aspect of hardness versus size of the part. Now, one thing I like over here is this hardness versus tempering temperature. We have our values in degrees Celsius and Fahrenheit, but we also have the hardness in terms of HB. That is a Bernal number, so we would have to go to the hardness standards, and you guys did that earlier in the ASTM standards, and we would need to convert Bernal to Rockwell C. The one thing I can look real quick here is, remember, we're getting above the lower critical, we're getting up here towards the upper critical the further we go over here, but look how fast as we heat this thing up, how fast the hardness draws down. And that's another word that we use, draw. So a lot of times we say we're going to draw the hardness down, put it in a drawing furnace. That is a term that metallurgists and people in industry will do, is let's draw the hardness down, put it in the drawing furnace. So basically we're doing that directly after our hardening on there. So you're going to have to probably convert that to temperatures in terms of anticipated values. Again, at the bottom, you have all the wonderful things. There's a lot of stuff about nitriding that we're not going to talk about that because it's not part of this lab. But again, we can see the effects of tempered martensite, annealed samples, and all that fun stuff through here. Let's go look at our A2 series. A2 is our tool steel, and to find that in Novel, you're going to go to the Heat Treater's Guide, and you're probably going to have to search for the A2 steels in the contents. Table of contents is probably the easiest way to find this one in there. Again, it's going to tell us some characteristics that this is a deep hardening steel, low distortion, very high safety. Remember we talked about safety and heat treating? That's this one. This is the nice one. 4140 may not be as safe. We'll see how safe it is through the lab when we actually heat treat it. But down here it talks about annealing this sample out. Over here it has hardening. And if I look at hardening, it's around a 62 to a 65 on the Rockwell C scale. That's hard. Remember we talked about a file being over 60? This stuff is going to really get hard. And guys, this is air hardening steel, so we can air harden it and air quench it. Isn't that amazing that we can get that kind of hardness out of there? So there's not a large delta T that's happening. That's going to make it a lot safer and not probably crack and distort near as much. Now down here we have a hardness versus tempering temperature for this steel, and they're nice to you. They put this in Rockwell C values for the tempering temperature. Again, it doesn't really drop down. That 4140 would drop way down real quick. Okay, this one stays pretty hard all the way up to these elevated temperatures above a 58. So man, this material is staying pretty hard for that. Now there's other tool steels like an H series that would really, and that's a hot working steel, so hot forging die steel materials, it would even hold its properties even better at these temperatures. So it's not going to temper as much till we get down here to this further temperature down here. And so that's going to kind of give you some ideas. And again, you could go through this thing, and this has tempering and dimensional changes that might come with this. We see a lot of the A2 tool steel making precision parts, heat treating in a protective atmosphere and holding tight tolerances and not seeing distortion or change that in the part. And again, you can see the nice, wonderful microstructures and learn about them and all the cementide carbides that are going to be associated with this wonderful steel. So I hope that helps you out, and watch the video on using the lab equipment pertaining this and take the quiz, and we'll see you guys in lab.